This is mathheals.com, where you can find more links to math and computer science YouTube videos. Let's take a look at centers of mass and moments of inertia. In our first definition, definition of mass of a planar lamina of variable density. If rho is a continuous density function on the lamina corresponding to a plane region R, then the mass m of the lamina is given by this formula. We've got our double integral, and R represents our region of integration of rho of xy, and that will give us our mass. So let's take a look at our first problem. Find the mass of the lamina, describe the inequalities given that its density rho of xy. I don't make rho very well, but looks like P is equal to xy. Hint, some of the integrals are simpler in polar coordinates, and this tells us that x is between 0 and 4, and y is between 0 and 3. Well, if we look at our formula, I need to set up our region of integration. If I look at this, here's our x and here's our y. X is from 0 to 4, and y is 0 to 3. So we're looking at this right here. And so to set this up, I'm going to go ahead and put the x value on the outside here. X is going to go from 0 to 4, and y is going to go from 0 to 3. It's a rectangle, so it's pretty easy setup. Now we need rho here, and rho is xy. And then y is the inner one, so this has to be dy, and then x is our outer one, so this has to be dx. Well, let's go ahead and do the inner integral first. It's going to go from 0 to 4. We're integrating with respect to y, so the x part is our constant. You can think of it that way. So for the y, we'll add 1 to our power divided by our new power. So we're going to have 1/2 x y squared from y is equal to 0 to y is equal to 3 dx. So we'll have x is equal to 0 to x is equal to 4. I typically put these variables here because it really does help you keep track of things. So you know exactly what you're plugging in. There's no mistakes in that form. You'll never see that in the book. They'll just have the numbers. Okay, so now, if I'm sitting here, I got two different variables. I'm wondering, what do I plug it in for? Well, y equals. Tells you exactly. So we're going to plug 3 in for the y. So we're going to have 1/2 x times 3 squared minus, and then we'll plug 0 in for the y. So we'll have 1/2 x 0 squared dx. Well, 0 squared is 0 times x is 0 times 1/2 is 0, so that all drops away. And 3 squared is 9 times 1/2 is 9/2, and I'm going to go ahead and put that out in front so I don't have to worry about it. And x equals 0 to x equals 4 of x dx. Well, add 1 to our power, divide by our new power, so we've got 1/2 x squared from x equals 0 to x equals 4. I can take the 1/2 and put it out in front so I don't have to worry about it. Now plug 4 in for the x, so I got 4 squared minus, and plug 0 in for the x, so I got 0 squared. Now this gives us 9/4, and 0 squared drops away, so we've got 4 squared, which is 16. So we've got 9/4 times 16, which gives us 36. Centers of mass and moments of inertia. So let me save that. Centers of mass and moments of inertia. page01.pdf. Now we're not going to go over all the physics part of what do these represent and everything. In this video I'm just going to show you how to find them. I'm definitely not a physics major. Okay, so let's look at our second example. Rho is xy still. And find the mass of the lamina again, so same instructions. X is from 0 to 2, and y is from 0 to square root of 4 minus x squared. Well, if I look at the graph of this, if I were to just set this equal, so y equals square root of 4 minus x squared, if I were to square both sides, I get y squared is equal to 4 minus x squared. Take the negative x squared over, and we get x squared plus y squared is equal to 4. So it's a circle of radius 2, which works out nice because we're looking at x from 0 to 2. Now, here we're saying that we're looking at y from 0 to this. Well, y is equal to 0 is this right here, and then that would be normally all the way across, but since we're only looking from 0 to 2, then it'll be the portion right here. Again, this is y is equal to a positive value, so we can't have it down here, obviously. And then we go from x equals 0 to 2, we're limiting it just to this side. I didn't draw that circle very well, but let's see. Let me give it another try. Not that it matters. Okay. So this is our region of integration. This right in here. Well, if I look at this, look at our formula. We're going to have x equals 0 to x equals 2. And then y is going to equal to 0 to y is equal to square root of 4 minus x squared. And then we have rho in the middle, which rho we said was xy. And then the y is our inner one, so this will be dy, and our outer one is dx. Now, whenever you have a circle of any form, whether it's a quarter of a circle, half a circle, or all the way around, it's easiest to switch it to polar. We'll start with the inner ones. R is going to equal to 0, and it'll go to r is equal to our radius, which is 2. Because if you think about it, r is equal to 0 is this origin, and then r is equal to 2, it goes out to here. Now, the outer one is going to be our theta. Now, our beginning angle is right here, and then it ends right here. Well, if I were to put an angle on this, this would be pi over 2. So this is going to go to theta equals pi over 2. Now, I need to change rho, the xy, to polar. And remember, x is equal to r cosine theta, and y is equal to r sine theta. So this becomes r cosine theta, r sine theta, when I replace the x and y. And when we switch it from rectangular to polar, we have to add an extra r on. That's the part I usually forget. Now the inner integration is the r, so this will be dr. The outer one is theta, so this will be d theta. Let me do a little bit of simplifying before we dive in with this. Let's see, r is equal to 0 to r is equal to 2. We have r, 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 so we got 3 r's. So we got r to the third. And then we got cosine theta, sine theta, dr, d theta. Well, if I work with my inner integral first, it's going to be from theta is equal to 0 to theta is equal to pi over 2. And we're integrating with respect to r, so the theta parts are constant, so they just stay there. I could even put them out in front of this integration symbol if I wanted to, but I'll leave them there, so they really don't hurt anything. Okay, so we're looking at the r. I got r to the third. I'm going to add 1 to my power, divide by my new power. So we're going to have 1/4 r to the fourth, and cosine theta and sine theta just carry along because they're our constant portion for now. And that's from r is equal to 0 to r is equal to 2. Well, the 1/4, I'm going to move clear out in front. Numbers you can freely take clear out in front. The cosine theta, sine theta, I'm going to put on front of the bracket. And I'm left with r to the fourth from r is equal to 0 to r is equal to 2. Okay, so we got m is equal to 1/4. Theta is equal to 0. Theta is equal to pi over 2. And then we got our cosine theta, sine theta. And we'll plug these in. So I'll plug in 2 for the r. So I got 2 to the fourth minus, and I'll plug 0 in for the r. So I got 0 to the fourth. Now 0 to the fourth drops away, and we got 2 to the fourth, which is 16, and I'll move it clear out in front. So I got m is equal to 1/4 times 16, and then the integral from theta is equal to 0 to theta is equal to pi over 2 of cosine theta, sine theta, d theta. Okay. Well, 1/4 times 16 is 4. Now if I look at the u substitution, if I let u equal to sine theta, the derivative of that, du, the derivative of sine is cosine, so we'll have cosine theta d theta. So this is going to become, and usually I don't actually switch my what I have here, my limits, my lower limit and my upper limit, bound, some books call it. I just switch what's in here, and then I'll put the u back in. So we said sine theta is u, so replace sine theta with u, and cosine theta d theta is du. Okay, so this is u to the first. We'll add 1 to our power, divide by our new power. So that's 1/2 u squared. Theta is equal to 0 to theta is equal to pi over 2. Take the 1/2 and put it out in front. So we got 4 times 1/2. And u up above we said was sine. So I'm going to plug that back in. So we got sine squared theta. Theta is equal to 0. Theta is equal to pi over 2. Well, 4 times 1/2 is 2. And now I'll plug in these. So I'll put in pi over 2 for theta. So I got sine squared of pi over 2 minus, and I'll plug 0 in for theta. So I got sine squared of 0. Well, if I look at my unit circle, sine of pi over 2 is equal to 1. So this is 1 squared minus sine of 0 is 0, so we'll have 0 squared. Well, 1 squared is 1 minus 0 squared, that's still 1, and 2 times 1 gives us 2. So that's our answer. I'll go ahead and save that. Tablet blows up every now and then. Okay, so 2. Okay, let's look at our next. Oh, sorry, I was changing myself around my seat. I went to the Y this morning, and kind of got me sore. Moments in center of mass of a variable density planar lamina. Let rho is. Obviously, I'm not an English major. Let rho be a continuous density function on planar lamina R. The moments of mass with respect to x and y axis are given by these moments. M sub x, that's a moment with regards to the x-axis, is equal to, and then we have y times rho. And a moment with respect to y is equal to the integral of x times rho. And then if m is the mass of the lamina, and that's still the same formula we saw before, then the center of the mass is given by this formula. If r represents a simple plane region rather than a lamina, the point is called the centroid of the region. So if you got a problem that's asking you to find a centroid, it's the same formula. Okay, let's take a look at an example. We got y is equal to square root of x, y is equal to 0, x is equal to 4, and rho is equal to ky. And it says find the center, the mass and the center of the mass of the lamina bounded by the graphs of the equation for the given density or densities. Hence, some of the integrals are simpler and polar. Pretty much for the examples I'm showing you, if it's a circle of some sort, switch it to polar. Otherwise, leave it in rectangular. Okay, so let's first just sketch this. Just see what in the world we're dealing with. X is equal to 4. Okay, so we're looking at a vertical line of 4. Y is equal to 0, that's the x-axis. And y is equal to square root of x. So our y is equal to square root of x looks like that with these other bounds. So this is our region of integration we're working with right there. Okay, well, first thing for our formula, before we even find these, we need m, because we're going to need that for this. I'm assuming. What are they asking? I'll eventually get there. Find a mass and center of mass. Okay, yeah, they're asking for the center of mass. So let's find m first. And there it is. Okay. So m. If we look at our x values, that's going to be from 0 to 4. And our y values will be y is equal to 0 to y is equal to square root of x. Now remember, for your mass, I need rho in the middle. So I'm going to put my ky here. And then my inner integral symbol is y, so this is dy. And then my outer one is x, so this is dx. Okay, so let's go ahead and do the inner integral. So we got x is equal to 0 to x is equal to 4. We integrate in respect to y. And the k I can go ahead and put out in front. Should have left a little bit more room for that, but I'll put the k out in front. Then the integral of y becomes 1/2 y squared. And from y is equal to 0 to y is equal to square root of x dx. And we got x equals 0 to x equals 4. You know, I'm just not leaving enough room here. The 1/2 we can put out in front, so I don't have to worry about it. So we got 1/2 k there. And we're left with y squared. And I'm going to plug in these values. So put in the square root of x for the y. So I have square root of x squared minus, I put 0 in for the y. So I'll have 0 squared dx. So we got m is equal to 1/2 k. X equals 0 to x equals 4. The 0 drops away, of course. Square root of x to the second power just gives you x. So this is x dx. Okay. So we've got 1/2 k. The integral of x, we add 1 to our power to divided by our new power. So we got 1/2 x squared from x equals 0 to x equals 4. The 1/2 I can put out in front. So that gives us 1/2 k times 1/2. And now plug in the 4 for the x. So I'll have 4 squared minus, and plug in 0 for the x. So I got 0 squared. Well, the 1/2 times 1/2 gives us 1/4. k. And that 0 drops away. 4 squared is 16. And 16 times 1/4 gives us 4. So m is equal to 4k. I guess we'll do the next one up here. We need the moment with respect to the x-axis. That's this one right here. And you notice that what you do is moment with respect to the x-axis, you plug in the other variable. We plug in y. The moment with respect to the y-axis, we plug in the other variable, plug in x. So it's pretty easy to remember. Okay. Now our region of integration never changes on these. So this is x equals 0, x equals 4. And this is y is equal to 0, y is equal to square root of x. And we're finding the moment with respect to x, we'll plug a y in, times rho. And rho is ky. And dy dx. Well, the k I can put clear out in front, like that. X is equal to 0 to x is equal to 4. And y is equal to 0 to y is equal to square root of x. Y times y is y squared. Dy dx. Okay, now let's do the inner integral. K stays out in front. X is equal to 0 to x is equal to 4. Y squared. We add 1 to our power, divide by our new power. So we've got 1/3 y to the third from y is equal to 0 to y is equal to square root of x dx. Okay. The 1/3 I can put out in front with the k, so we got 1/3 k. And x is equal to 0 to x is equal to 4. And we're left with y to the third, so we'll plug the square root of x in for y. So we got square root of x to the third power minus, and we'll plug 0 in for y. So we got 0 to the third dx. And we got 1/3 k. X is equal to 0 to x is equal to 4. Square root of x, that's x to the 1/2 to the third power dx. The 0 drops away, which gives us 1/3 k, and then from x is equal to 0 to x is equal to 4, and x to the 3/2 power. You raise one exponent to another exponent, you multiply them. And now we're ready to take this integral. So I got the 1/3 k carrying down. Now we'll add 1 to our power, divide by our new power. So we're going to have 2/5 x to the 5/2 from x equals 0 to x equals 4. Now 2/5 I can put out in front. So I got 1/3 times 2/5 k. And I'll plug in these numbers. So I got 4 to the 5/2 minus, I'll plug 0 in for x, I got 0 to the 5/2. Well, 1/3 times 2/5 gives us 2/15 k. And this 4 to the 5/2, I can rewrite that as 4 to the 1/2 raised to the 5th power. Now 4 to the 1/2 is the square root of 4, which is 2. 2 to the 5th gives us 32. So our moment with respect to x is going to be equal to 64 over 15. Okay. Okay. Now let's find our moment with respect to y. Well, our moment with respect to y, the region of integration is still going to be the same. So I got x equals 0 to x is equal to 4. And y is equal to 0 to y is equal to square root of x. And the moment with respect to y, I need to put an x in here. Remember, you always put in the other variable. And then rho, which was ky, dy dx. Now I'm going to do the integral here. And the k I'll go ahead and put out in front. So I got k there. And then x is equal to 0 to x is equal to 4. I'm integrating with respect to y, so the x part is like a constant. So I just look at the y. Add 1 to your power, divide by your new power. So that gives us 1/2 x y squared from y is equal to 0 to y is equal to square root of x dx. Now the 1/2 I can put clear out in front. So we got 1/2 k, and then x is equal to 0 to x is equal to 4. And the x I can put out in front of the bracket, because it's a constant portion when we're integrating with respect to y. And now we're ready to plug in our items here. So I got 1/2 k. These are kind of running together. There we go. And then from x is equal to 0 to x is equal to 4. And I'll plug in the square root of x for y. So I'm going to have the square root of x squared minus, and plug 0 in for y. So I got 0 squared dx. So that carries down 1/2 k, and then x is equal to 0 to x is equal to 4. Now, square root of x, the second power, the square root and the second power cancel each other, so that gives me x, and x times x gives me x squared dx. Okay, so now I'm ready to take the integral of x squared, which gives us 1/3 x to the third. Add 1 to your power, divide by your new power. X equals 0 to x equals 4. 1/3 I can put out in front. So I'm going to have 1/2 times 1/3 k. And now plug in these values. I plug in 4 for the x. So we've got 4 to the third minus, and put 0 in for the x. So I got 0 to the third. So that gives us 1/6 k times 4 times 4 is 16, times another 4 is 64, I believe. Which gives us 64 over 6k, which is 32 over 3k. Okay. Well, now we got everything we need. So for our center of mass, it's equal to this. So m sub y over m, and m sub x over m. M sub y, that's 32 over 3. So 32 over 3k over m, which was 4k. And m sub x is 64 over 15k over 4k. K's cancel. And then this 3 here goes down with this 4. When you have a single fraction up on top, you can take its denominator, put it with the other denominator. So that becomes 32 over 12, 3 times 4. And then this one will be 64 over, and again, if you have a single fraction up on top here, you can take that denominator, put it down with the other one. 4 times 15 gives us 60. And let me see, those are both divisible by 4 at least, so that gives us 8/3. And what are these, both divisible by 4? I think so. 24, 16. Divide that by 4, and I get 15. So that would be our center of mass. And the other thing they were asking for was mass. This was the first thing they were asking for. So those are answers. These are not necessarily the shortest problems. Let me save that. And let's look at our next problem. Find the mass and center mass again. Okay, so we've got y is equal to 1 over x. Y is equal to 0, x is equal to 2, x is equal to 6, and rho is equal to kx squared. Grab a drink here. Now if I sketch it, we're looking from x is equal to 2, 4, 5, 6, to x equals 6. And y is equal to 0 would be this. So we got these bounds so far, and y is equal to 1 over x. Looks something like that. Doesn't have to be exact, but I can see that this is my region of integration right in there. Okay, so we need to find our m. So m is going to go from x is equal to 2, x is equal to 6, and from y is equal to 0 to y is equal to 1 over x of rho, which is kx squared, dy dx. Okay, so I'll do the first, the inner integral. The k I'll put out in front. And this will be x is equal to 2 to x is equal to 6. And we're integrating with respect to y. There is no y's, is there? So the x squared is considered like a constant. If we had just like a number there, like 5, then we just add a y onto it. And that's what we'll do here. So we got x squared y from y is equal to 0 to y is equal to 1 over x dx. And now the x squared I can put out in front of the brackets. It's a constant portion. And the y, I'll plug the 1 over x in for y, minus, and I'll plug 0 in for the y, dx. Okay, so we got k, and then x is equal to 2 to 6. Now the 0 drops away. X squared times 1 over x will give me x squared over x, or just x dx. Okay, so now we'll take the integral of x, which is 1/2 x squared. You add 1 to your power, divide by a new power. From x equals 2 to x equals 6. The 1/2 I can put out in front, so we got 1/2 k. And I'll plug in a 6 for the x, so we got 6 squared minus, and I'll plug 2 in for the x, so we got 2 squared. So we got 1/2 k. 6 squared is 36, minus 2 squared, which is 4. The 36 minus 4 is 32, times a half gives us 16. So our mass is 16k. Okay. Let me come up here. And there we go. Let's find our moment with respect to x. Okay, so our moment with respect to x, we're going to go from same region of integration, x equals 2 to x equals 6, and y is equal to 0 to y is equal to 1 over x. Now we're finding the moment with respect to x, we have to add a y. You always add the other variable, times rho, which was kx squared. And then dy dx. Well, let's find the inner one. Again, the k I can put clear out in front. And I got x equals 2 to x equals 6. And we're left with yx squared. And I'm integrating with respect to y, so the x squared just carries along. So we look at the y, we add 1 to our power, divide by our new power. So we're going to have 1/2 y squared x squared from y is equal to 0 to y is equal to 1 over x dx. 1/2 I'll put clear out in front. So I'm going to have 1/2 k x equals 2 to x equals 6. And I'm left with the y squared, x squared there. But the x squared is a constant when integrating in respect to y, so I'll put it out in front of the bracket. And I'm left with y squared. Now I'll plug 1 over x in for y. So I got 1 over x squared minus, and I'll plug 0 in for y. So I got 0 squared dx. Well, the let me write this down. 1/2 k x is equal to 2 to x equals 6. The 0, of course, drops away. The 1 over x, the second power, gives us 1 over x squared. 1 over x squared times x squared gives you a 1. So we've got 1 dx. Now integrate in respect to x. The 1/2 k stays there. This becomes 1x, or just x, from x equals 2 to x equals 6. And now plug 6 in for the x, minus, I'll plug 2 in for the x. Now 6 minus 2 is 4. 4 times a half is 2, so we got 2k. Okay, so now let's find a moment with respect to y. Region of integration is still the same, so it's going from x equals 2 to x equals 6, and y is equal to 0 to y is equal to 1 over x. We're finding a moment with respect to y, so we have to put an x in there, times rho, which is k x squared, dy dx. Well, the k I can put clear out in front, and let me write it down again. X is equal to 2 to x equals 6. Y is equal to 0 to y is equal to 1 over x. And x times x squared gives us x to the third. dy dx. Okay, now we're working with the inner integral. And we're integrating with respect to y, but there is no y, which makes it easy. So k stays there. X is equal to 2 to x is equal to 6. And this just becomes x to the third y. Again, if you integrate in respect to y, this is considered like a constant portion, so you just add a y next to it. From y is equal to 0 to y is equal to 1 over x dx. And I got k, x is equal to 2, x is equal to 6. Now we'll plug the actually the x to the third I can put on in front of the bracket. Now we're going to plug 1 over x in for y. So we've got 1 over x minus, now plug 0 in for y. So that gives us 0 there. Okay. Well, 0 drops away. X to the third times 1 over x is x to the third over x, or x squared dx. And now we'll find the integral again. K stays out in front. X squared, add 1 to your power, divide by new power. So we got 1/3 x to the third. From x equals 2 to x equals 6. Put the 1/3 out in front, so we got 1/3 k. And now I'm going to plug in the 6 for the x. So we got 6 to the third minus, I'll plug 2 in for the x. So we got 2 to the third. Where's my calculator? Ooh, there it is. 6 to the third. 36 times 6. 6 to the third. 216. So that's 216 minus 2 to the third is 8. So that gives us 208 over 3k. Okay. Well, now we're ready to find our center of mass. X bar or Y bar is going to equal to, don't remember. Let's go look. Okay. Moment with respect to Y over M, and then moment with respect to X over M. Moment with respect to y is 208 over 3 k over m, which was 16k, comma, moment with respect to x is 2k over mass, which is 16k. Now, of course, the k's cancel, and this becomes 208 over, remember, if you have a single fraction up on top here, you can take that denominator, put it down with this one. 3 times 16 is 48. And these k's cancel, and 2/16 gives us 1/8. And these are both divisible at least by 4, maybe more than that. That goes into that 5, 2. Let's see, 4 is 5, 2, and then goes into there 1, 2, 1/8. And still both divisible by 4, so that gives me 1/13 thirds and 1/8. Assuming no basic math error, which I'm very bad at, so it wouldn't shock me if you wouldn't find 1 or 2 in this video with basic math errors. Okay, let me go ahead and save this now. And let's look at our next problem. How many more of these we got? 4. Wow. I think the last one is a polar. Yeah, it is. Okay, so we got y is equal to e to the x. Y is equal to 0. X is equal to 0. X is equal to 1. And rho is equal to kx. And we'll grab a drink here. Okay. First off, let's kind of graph this. Y is equal to e to the x. Kind of goes up like that. Y is equal to 0 is the x-axis. X is equal to 0 and x is equal to 1. We're looking at this. This is our region of integration. Okay. So let's find m. We're going to have x equals 0 to x equals 1. And y is equal to 0 to y is equal e to the x. And then we want rho in here, which is kx dy dx. Okay, so let's work with the inner integral first. Work with that. Actually, I guess I could put the k out in front, but oh well, I'll do it the next step. Okay, we integrate in respect to y. There is no y. So this just becomes kxy. Y is equal to 0 to y is equal e to the x dx. I'm going to put the k out in front. X is equal to 0. X is equal to 1. And the x I can put out in front of the brackets. And now we'll plug these in for y. So put an e to the x for the y, minus, and put 0 in for the y, dx. And, not sure if I have room. Okay, let me put it right below here. This is integration by parts. And we get x e to the x. So the d column will contain our x. It's a part that when you take a derivative, it'll disappear. The derivative of e to the x is e to the x, so it would never disappear. Well, the derivative of x is 1, and the derivative of 1 is 0. This always starts at plus, minus, plus. And the integral, or e to the x will go there. The integral of e to the x is e to the x, and the integral of e to the x is e to the x. And this is the flow of our table. Okay, so I'm going to have m is equal to k, and then this part right here, if I follow this, plus x e to the x, so we're going to have x e to the x, and then we have a minus 1 times e to the x, that's minus e to the x, from x equals 0 to x equals 1. Okay. So if we plug in our values, put 1 in for the x. So I'm going to have 1 times e to the first minus e to the first minus, now put parentheses because this has to change the sign of everything that follows it. And I put 0 in for x. So I got 0 times e to the 0 minus e to the 0. 1 times e is e. Minus e gives me 0. That's interesting. That drops away. Minus 0 times that drops away. And then e to the 0 is 1, so this is a negative 1. Which negative negative gives me a positive 1. So m is just equal to 1k or k. That one worked out nice. Made me think I screwed it up. It worked out so nice. Let me check. Yeah, that seemed to make sense. Yeah? Okay. Of course, you have to remember the little table method for finding integration by parts. There we go. Now let's find our moment with respect to x. So moment with respect to x is going to be from x is equal to 0 to x equals 1, y is equal to 0 to y is equal e to the x. Region of integration doesn't change. And then moment with respect to x, we throw a y in there times rho, which is kx. dy dx. I'm going to put the k out in front. X equals 0 to x equals 1. And we're integrating with what's inside the inner one here, which is the integrate in respect to y. So the k is a constant, so we look at just the y. So this becomes 1/2 y squared x from y is equal to 0 to y is equal e to the x dx. Well, the 1/2 I'll put out in front. So we're going to have 1/2 k, and then we'll got x equals 0 to x equals 1, and we'll plug these, the x I can put out in front of the brackets, and we'll plug these in for y. So we're going to have e to the x squared minus, and put that in for y, so 0 squared dx. Okay, so we got 1/2 k, x is equal to 0 to x is equal to 1, and we're left with x e to the 2x dx. We have to use it by parts again. So I got my column SDI. The part that will disappear with taking derivative is your d column, which is the x. Derivative of x is 1, derivative of 1 is 0. This is always plus, minus, plus. It alternates. Now our integral, e to the 2x. Now you have to use the u substitution here. And the if I let u equal to 2x, du would be 2 dx. So we need a 2 inside, so we offset it with a 1/2 out in front. So taking the integral of that, that'd give us 1/2 e to the 2x. And taking the integral again, put another 1/2 out in front. 1/2 times 1/2 gives us 1/4 e to the 2x. If I have room down at the bottom, and actually remember, I'll show you that integration at the end of this problem. I don't want to take space right now because I'm not sure if I'm gonna have room. And again, this is our flow, so it goes over like that, down to there, and then over to here, and then down to there. So we have our 1/2 k here, and then we're going to have x 1/2 e to the 2x. So we got 1/2 x e to the 2x, and we've got a minus 1/4 e to the 2x. The 1 doesn't actually do anything there. from x equals 0 to x equals 1. We're ready to plug in those numbers. So we've got 1/2 k there. We'll plug 1 in for x. So we've got 1/2 times 1, e to the 2 times 1, minus 1/4 e to the 2 times 1, minus, and then we'll plug 0 in for x. So I got 1/2 times 0 e to the 2 times 0, minus 1/4 e to the 2 times 0. Okay, so I got 1/2 k. Now here, 1/2 times 1 is 1/2, and so that's 1/2 e squared, minus 1/4 e squared, minus this 0 times 1/2 times e to the, that power drops away. So we got a negative negative, which becomes a positive 1/4, and 2 times 0 is 0, so e to the 0 is 1. Okay, so want to get a common denominator here, since these are both e squared. So this becomes 2/4 e squared minus 1/4 e squared plus 1/4. So we got 1/2 k times 1/2. Wait, what am I doing? Scratch, scratch, scratch. Okay. 2/4 minus 1/4 is 1/4. So we got 1/4 e squared plus 1/4. Now k I'll leave out in front, but I'll go ahead and multiply the 1/2 through. Maybe. I'm lying to you. I'm going to go ahead and factor it out in front. I'll take these 1/4 out in front, and that gives us 1/8 k e squared plus 1. Now I don't know which way it'll be the simplest form. It'll make more sense once we put it into the fraction. Now, assuming I didn't make a basic math error somewhere along the way, that's our moment with respect to x. Well, let's find our moment with respect to y. There we go. Okay, so I'll go from x equals 0 to x equals 1 again, and y is equal to 0 to y is equal e to the x. Now I'm finding the moment with respect to y, so I have to put an x in there, times rho, which was kx, dy dx. Now the k I'm going to go ahead and put it clear out in front. And the work with the inner integral, we're integrating with respect to y, there is no y. Now x times x is x squared, so we're going to have an x squared, and we have to put a y on there. From y is equal to 0 to y is equal e to the x dx. X equals 0 to x equals 1. The x squared I can put out in front of the bracket. And I'll plug these in for y. So I'll put e to the x in for y, minus, put 0 in for the y, dx. Which is going to give us k times the integral from x equals 0 to x equals 1 of x squared e to the x dx. This is another by parts. So we're going to have our s di. And x squared is a part that will disappear. So we got x squared, derivative of that is 2x, derivative of that is 2, derivative of that is 0. This will be a plus, minus, plus, minus. Integral of e to the x is e to the x. Integral of e to the x is e to the x. Integral of e to the x is e to the x. So our flow on this will go like this. Okay, so k is there. And then I got plus x squared times e to the x, so that's x squared e to the x. Negative 2x times e to the x, so minus 2x e to the x, plus 2 e to the x. From x is equal to 0 to x equals 1. Well, now we're ready to plug those in for x. So put the 1 in for x first. Okay, so I'm going to have 1 squared e to the first power minus 2 times 1 e to the first power plus 2 e to the first power minus, and then parentheses because that's flips on everything, I put 0 in for x. So I get 0 squared e to the 0 minus 2 times 0 e to the 0 plus 2 e to the 0. So k carries down. Did I not bring any number out of that? I guess I never did I? Okay. So 1 squared is 1 times e is e minus 2 times 1 is 2 e. Assuming that's an e. Yeah. So minus 2e plus 2e minus, that drops away, that drops away. E to the 0 is 1, so this is 2. Like that. Negative 2e plus 2e cancels, and we got e minus 2. And that's our moment with respect to y. Assuming I didn't make any kind of math error, which is very possible. Okay, and our center of mass. No memory, no memory. Okay. M sub y over m sub x over m. M sub y was this one. So I got k times e minus 2 over m, which was k. And then m sub x is this one. So we got 1/8 k e squared plus 1 over k. Now k is going to cancel, and we're going to have e minus 2, comma, 1/8 times e squared plus 1. Assuming no basic math error anywhere. That's our center of mass. So let me go ahead and save that. There we go. And let's look at our next problem. Okay, so we got x squared plus y squared is equal to 9. X is greater than or equal to 0. Y is greater than or equal to 0. And rho is equal to k times x squared plus y squared. It says find the center mass and center of the mass of the lamina bounded by the graphs. So same instructions. Now x squared plus y squared is equal to 9 is a circle of radius 3. And that kind of tells you something right there. But specifically, this says we're only looking where x is greater than or equal to 0 and y is greater than or equal to 0. Which means only this part of the circle. So that's going to be our region of integration right there. And I can go ahead and do the setup directly on this. I don't need to write down the rectangular for m. Okay, so we're going to have m is equal to, and notice how my r is going to go from r is equal to 0 to r is equal to 4. And theta is 0. Now r is equal to 0 to r is equal to 4. It goes to your radius, which is 4. And this is our beginning angle, and then it ends right here, which is pi over 2. Now if you had a different problem that went clear over here, then it'd be pi. But this will go to theta is equal to pi over 2. Now we're going to have rho in here. Now rho is this. And remember that r squared is equal to x squared plus y squared. So the k is going to remain. And then this gets replaced by r squared. So that's our rho. Now remember, when we switch it to polar, we have to add on an extra r. So then dr d theta. Okay. Well, let me simplify that a little bit. Take the k, put it out in front. And theta is equal to 0 to theta is equal to pi over 2. R is equal to 0 to r is equal to 4. R squared times r is r to the third. Dr d theta. I'm going to work with the inner one. So k, and then theta is equal to 0 to theta is equal to pi over 2. The integral of r to the third. Add 1 to your power, divide by your new power. So we've got 1/4 r to the fourth from r is equal to 0 to r is equal to 4 d theta. Now the 1/4 I can put clear out in front. So we got m is equal to 1/4 k. Theta is equal to 0 to theta is equal to pi over 2. And now we'll plug 4 in for r. So we're going to have 4 to the 4th power minus, plug 0 in for r, so 0 to the 4th power, d theta. Now the 4 to the 4th I could put out in front. So we're going to have 4 to the 4th over 4k, and the 0 of course drops away. Theta is equal to 0 to theta is equal to pi over 2 d theta. Now there's an invisible 1 left in there, so when I take the integral of it, it's just theta. And this becomes 4 to the third. You have 4 to the 4th over 4 to the 1st, k. And we said that the integral of that is theta, from theta is equal to 0 to theta is equal to pi over 2, which is 64k times, and we'll plug this in for theta. So pi over 2 minus, and plug 0 in for theta, which gives us 64 divided by 2 is 32 pi k. And that's our mass. Well, let's find our moment in respect to x. Well, remember something about our moment with respect to x. Our moment with respect to x, we're going to have our region of integration here, and we put an extra y in here, times rho. So y, well first, x is equal to r cosine theta, and y is equal to r sine theta. Go away fast. So when we do the setup on this, it's still theta is equal to 0, theta is equal to pi over 2. It's still r is equal to 0 to r is equal to 4. But we got a y in here, and y we said was r sine theta, so we have to put that in there. So we got r sine theta times rho, which is k, and remember we can replace the x squared plus y squared with r squared. So k r squared. And then that's dr d theta. Okay, well, we'll put the k out in front. Theta is equal to 0 to theta is equal to pi over 2. Do a little bit of simplifying. R is equal to 0 to r is equal to 4. And we have r times r squared, which is r to the third, and sine theta. Dr d theta. Okay, so now we're going to work with our inner integral. This one right here. So k carries down. Theta is equal to 0 to theta is equal to pi over 2. And we're integrating with respect to r, so this becomes 1/4 r to the 4th sine theta, from r is equal to 0 to r is equal to 4 d theta. Now the 1/4 I can put clear out in front, so we got 1/4 k. The sine theta I can put out in front of the bracket. And that leaves us r to the fourth inside. So plug in our 4 for our r, so we got 4 to the fourth, minus, and plug 0 in for r. So we got 0 to the fourth, d theta. I already did it on the first part here, when I take the 4 to the fourth out in front, and we know that gives us 64. So that's going to give us 64k. And then we got theta is equal to 0 to theta is equal to pi over 2 of sine theta, d theta. So we got 64k. Now the integral of sine is negative cosine theta, from theta is equal to 0 to theta is equal to pi over 2. Now plug in those values. So we're going to have 64k, and then negative cosine of pi over 2 minus a negative cosine of 0. So we got 64k. Cosine of pi over 2 is 0, so that drops away. Here we got negative negative, which becomes positive, and cosine of 0 is 1. So this is actually our moment with respect to x. Okay, and now let's find our moment with respect to y. Okay, so moment with respect to y. And again, remember, that's going to be our region of integration. We have to throw an x in there, times rho. So it's going to be theta is equal to 0 to theta is equal to pi over 2. R is equal to 0 to r is equal to 4. And we got an extra x in there, but x is r cosine theta. So we'll put r cosine theta in there. And did I screw up in this last one? I'd be mad if I did. I did, didn't I? You have to put an extra r in there. I don't know how many times I'm going to forget that. Okay. Well, remember, when you change it to polar, you have to put an extra r, which means this will be r to the fourth. Sorry about that. And then that'll be 1/5 r to the fifth. Get that tattooed in the middle of my forehead. I can't seem to remember that. Okay, so 1/5 r to the fifth. And then we'll have down here the 1/5 comes out. And this will be that. And that's 4 to the fifth, 0 to the fifth. I would work off of a script, but then it'd be boring to me, and I wouldn't do it anymore. Okay, so then that's going to change the number out in front. 64, 64, 64. Okay, I'm going to do this in my calculator. 4 to the fifth, 4 caret 5 is 1024. So this will be 1024 divided by 5, because 4 to the fifth is 1024. So we've got 1024 over 5, 1024 over 5. Which gives us 1024 over 5k. Okay. I'll try not to screw that up on this next one. Okay. Now this x, that's our r cosine theta. And now we need rho, which we said was k r squared, and we need an extra r, because when you change it to polar, you have to have that. dr d theta. Take the k, put it out in front. Theta is equal to 0. Theta is equal to pi over 2. And then r is equal to 0 to r is equal to 4. And do a little bit of simplifying. We got r times r squared is r to the fourth. That's interesting. Is that, will that, yeah, that makes sense. Okay, so we got r to the fourth, cosine theta, dr d theta. Well, we're going to find that basically we're integrating with respect to r to the fourth again, which is what we just did over here. I wouldn't normally go through the steps again, but since I screwed it up on the first one, then let me see if I can screw it up again here. Okay, so we're going to add 1 to our power divided by our new power. So we're going to have 1/5 r to the fifth. Cosine theta just carries along from r is equal to 0 to r is equal to 4. D theta. The 1/5 I'll put out in front. So we're going to have 1/5 k. Theta is equal to 0 to theta is equal to pi over 2. We'll put the cosine theta out in front of the bracket. And now we're left with r to the fifth. So I'll plug in these values. So I'm going to have 4 to the fifth minus 0 to the fifth. D theta. We already said r to the fifth is 1024. Or r 4 to the fifth is 1024. So I'll put it out in front. I have to go pick my son up here in a little bit. That's also another thing's panicking me. Theta is equal to 0. If I had known how long this video was going to take, I wouldn't have started it. Cosine theta, d theta. Okay, so now we're going to find the integral of that. So the 1024 over 5k, and then the integral of cosine is sine. From theta is equal to 0 to theta is equal to pi over 2. Plug those in, and we got 1024 over 5k, and we'll plug in the pi over 2 for theta. So we got sine of pi over 2 minus sine of 0. Well, sine of 0 is 0, so that drops away. Sine of pi over 2 is 1, and 1 times that gives you, oh, that's interesting. Same thing. Kind of makes sense when I think about it, now that they're a circle. So then our center of mass, x bar, y bar, is going to equal to, I think I'd have this memorized, m sub y, moment with respect to y over m, and moment with respect to x over m. So this will be 1024 over 5k over 32 pi k, and this will also be 1024 over 5k over 32 pi k. Well, k is going to cancel, and this 5 I can put out down in the denominator with that. So we're going to have 1024, 32 times 5 is 160 pi. And this one will be the same. So 1024 over 160 pi, and I'm going to use my calculator to simplify this real fast. By 160, math, enter, 32/5. So this becomes 32 over 5 pi, and this is 32 over 5 pi. And that's our answer. Let me go ahead and save that. And the next part talks about our moments of inertia, about the x-axis, about the y-axis, our polar moment of inertia, radius of gyration, about the x-axis and y-axis. And so let's go ahead and look at a problem. If I start running out of time, I may just do the setup, so you see that. Okay, so find moments of inertia, and so let's find these first. So we need our picture to find the region of integration, and that's a rectangle, so it's a pretty straightforward one. So our region of integration is going to be based upon x equals 0 to 3. and y goes to 5. Okay. So this is going to go from x is equal to 0 to x equals 3. And this will go from y is equal to 0 to y is equal to 5. Now, the moment of inertia about the x-axis, we put a y squared in there. So we've got a y squared times rho, and they tell us in this that rho is equal to 1. And then dy dx. So let's find that first. So this is going to be x is equal to 0 to x is equal to 3. We'll add 1 to our power, divide by our new power. So we've got 1/3 y to the third from y is equal to 0 to y is equal to 5 dx. And now I'll save some steps here. We're plugging 5 in for the y and 0 in for the y, and 1/3 I can put out in front. So this is going to give us x equals 0 to x equals 3. 5 to the third is 125 dx. Now I can put that clear out in front. So we got 125 over 3. And then the integral, since there's nothing left in here, it'd just be x from 0 to 3. Which would give us 125 over 3 times 3 minus 0, which gives us 125. Okay. Now if we now you'll find that here we're finding the inertia with respect to x, we put a y squared in here. If we're finding the other one with respect to y, you put an x squared in there. So it's kind of flows. So this one, same region of integration, x equals 0 to x equals 3, and y is equal to 0 to y is equal to 5. And we're going to put an x squared in here, times rho, which was 1, dy dx. So we're going to do that one. So we've got x is equal to 0 to x is equal to 3. And that becomes, integrate in respect to y, there is no y, so this becomes x squared y from y is equal to 0 to y is equal to 5 dx. Now if we plug these in for our y, so we'll have plug 5 here, we get 5x squared. Plug 0 in here, we get 0x squared. So this becomes x equals 0 to x equals 3 of 5x squared dx. Add 1 to our power, divide by our new power. So we're going to get 5/3 x to the third from x equals 0 to x equals 3. Now 0 is going to drop away, so we don't need to worry about that. If I put 3 in there, 3 to the third is 27. So we got 5 to the third times 27, which is 45. What were they finding? Find the moments of inertia. Okay, and then the other ones. And this is going to be the square root of this. I guess we need m also, don't we? Okay. So come down here. M is going to be x equals 0 to x equals 3. And then y is equal to 0 to y is equal to 5. And rho, which was 1, dy dx. So we'll do the integral here. Hopefully you've seen enough examples in the beginning of this video. You don't need to see all the steps here. But that'd be y from y is equal to 0 to y is equal to 5 dx. If I plug 5 in for y and 0 in for y, that gives us the integral x equals 0 to x equals 3 of 5 dx, which gives us 5x from x equals 0 to x equals 3, which ends up giving us 15. So m is equal to 15. Okay, let's come back up to here then. And this is going to be I sub y, which is 45 over 15. which is going to give us the square root of 3. Now these are the, what is these, radius of gyration? Radius of gyration. So our other one is going to be the square root of I sub x over m, which is going to be 125 over 15, which gives us 25 over 3, which would give us 5 square root of 3 over 5 over square root of 3, which gives us 5 square root of 3 over 3. So let me go ahead and save that. And on this one, I'm just going to do the setup since I am running out of time. I think you get the idea. Now this one's the entire circle, isn't it? And again, so if it's a circle, then your polar is going to be your best way to set it up. So our region of integration, I'm just going to look at that. It's going to be r is equal to 0, and our radius is 2. So it'll go to r is equal to 2. Theta is going to go to from 0, and it goes all the way around the circle, which is 2 pi. So that's going to be our region of integration of all of these. Now our inertia with respect to x is this formula right here. So we need our region of integration. Theta is equal to 0 to theta is equal to 2 pi. R is equal to 0, R is equal to 2, and we need a y squared in there. Well, remember, x is equal to r cosine theta, and y is equal to r sine theta. So we said we need a y squared in there. So for the y squared, I'm going to have r sine theta squared. So that's our y squared. And then we have it times rho. This problem, again, rho is 1. And the thing I seem to forget is to put an extra r here. And then we'd have dr d theta. What if I can do this real fast? I'll skip some steps. Theta is equal to 0. Theta is equal to 2 pi. So this gives us r squared sine squared. So we got r squared times r, which is r to the third. So that gives us 1/4 r to the fourth sine squared, like that, d theta. And that's from r is equal to 0 to r is equal to 2. If I plug 2 in there, 2 to the fourth is 16 times 1/4 is 4. So I can put that out in front. Theta is equal to 0. Theta is equal to 2 pi. And we're left with sine squared inside here. But sine squared is equal to, I haven't forgot. I'm going to go get him here in just a second, okay? He wants to do something. Oh, okay, well, I'll hurry up. I'm just going to do the setup on these. So it's my wife bugging me. Okay, sine squared is equal to 1 minus cosine 2 theta over 2. That's one of our identities. And d theta. And I've actually worked this one out because I want to make sure I knew how to handle a sine squared. So I'm going to skip a few steps here, and this is equal to 4 pi. Okay, well, let's do our setup for inertia with respect to y. Again, it'll be from theta is equal to 0 to theta is equal to 2 pi. R is equal to 0 to R is equal to 2. And I'm going to have an x squared in here. Remember, x is equal to r cosine. So this will be r cosine theta squared times rho, which is 1, with an extra r in there. Dr d theta. And then if I go through and solve this, do I got I sub y? Oh, I don't. I didn't do that one. Well, again, it's the 1/4. Same thing as this. So that gives us 2. So we have a 4 out in front. Oh well. I'll leave that. Of course, you need m. And that'll be theta is equal to 0. I wouldn't break my son's heart for any amount of money. R is equal to 0 to R is equal to 2. And then we need rho in here. Rho is 1. Now we need the extra r that I seem to always forget. And then dr d theta. And that'll give you whatever. And then after you get those, then let's see, what is this? The other one, I think. Yes, it is. Over m. So you plug it into there, and you plug it into there. So that should be pretty hopefully obvious how to do that. Let me go ahead and save the setup on that, and then we'll write the setup on the last one. Maybe someday I'll go back and re-record this. Or actually finish the problems. Okay, our last problem is asked us to find these right here, and it asks us to find an additional one here. This one is just adding our initial about the x and initial about the y together. So nothing exciting there. And I don't think I actually set this one up. It's 9 minus x squared. Y is equal to 0. X is greater than 0. Rho is equal to kx. Now if I look at the graph of this, 9 minus x squared, so it comes up here, 9 comes down like this. And we got y is equal to 0 here, and then x is greater than 0. So it'd be this piece right here. This is our region of integration. Now to figure out what your x is, you want to find the intersection of 9 minus x squared and this right here, which is y is equal to 0. So we get 9 is equal to x squared, x is equal to plus or minus square root of 9, or x is equal to plus or minus 3. So it's obviously 3. So our region of integration for this, for m, we're going to go from x is equal to 0 to x is equal to 3, y is equal to 0 to y is equal to 9 minus x squared, times rho, which is our kx, dy dx. So that's m. Now our inertial about x, we're going to have x is equal to 0 to x is equal to 3, and then y is equal to 0 to y is equal to 9 minus x squared. Now we're finding with respect to x, we have to put a y squared in here, times rho, which was kx, and then dy dx. Now our setup for the inertial with respect to y, that's going to be x is equal to 0, x is equal to 3. I'll have to get dressed here real quick. And then this will be x squared, but I'm gonna be on time. I'm gonna be a hero to him. Dy dx. And these give you whatever. And then after you get those, then you're going to find this, and that's going to be adding those two together. And then this will be the square root of I sub y over m. And then our last one will be the square root of I sub x over m. And that'll give us our answers. So I'm going to go ahead and save that and go get my son. I do apologize for not finishing those. I just never assumed this one would take me so long when I started this video. But I think you've seen enough examples earlier on that these will be a piece of cake for you to actually solve. Okay, and that was centers of mass and moments of inertia.